In this session, I'm going to be talking to you about microservices challenges and how to overcome those challenges using perfect design patterns. Before we dig deep, let us understand modern distributed computing. So, computing power is no longer centralized but spread across connected systems worldwide, and the foundation of which lies in distributed infrastructure, which enables scalability, resilience, and speed. We have data centers that are spread across the globe, which house thousands of machines working together. These machines are known as compute nodes, where physical servers, virtual machines, or containers perform workloads in parallel across a high speed network. On top of which, we have storage systems like distributed databases, object stores, and file systems, which manage enormous volumes of data with redundancy and global accessibility. Finally, we have tools like Kubernetes, Terraform, and OpenStack, which orchestrate and automate everything for us, and it also has self healing operations. Together, these layers form the heart of modern distributed computing, which powers the cloud, edge, and the connected world that we live in today. In distributed computing, every system revolves around three key elements: data, logic, and computation. Data is the foundation, which is stored, replicated, and shared across multiple nodes to ensure availability and consistency. Logic defines how that data is processed, and computation is the engine, executing tasks across different clusters and containers to deliver performance at scale. Together, these three pillars create the framework for modern distributed applications, which are fast, reliable, and intelligent. The software architecture that leverages the distributed infrastructure the most is microservices architecture. Microservices are independent autonomous modules that has following attributes. Every microservice runs in its own process or container. It has its own data store and communicates with others via lightweight APIs. These microservices can be developed, deployed, and scaled independently. Major challenges of microservices architecture. First is decomposition. A new software system or an existing software system, we need to clarify and define the boundaries between various services that fit together to form a larger software system. Second is communication. Service communication happens over the network, and communication between services has various trade offs that we need to address. It can be sync communication or async communication. Next is data consistency. Each service should have its own database, which is a norm, but the system as a whole should be having consistent views of the overall data. Trade off here is between strong consistency and eventual consistency. Tracing errors and observing the resources in a distributed system spanning across several microservices is difficult. So, we will address this as well. Last is distributed transactions. Since transactions can encompass various services, so it becomes tedious to manage. We need special retry logics and write compensation transactions for failures. Let's go deeper into these challenges one by one and see the resolution patterns for all of these. Breaking the monolith into microservices is the challenge. We can address it using three main patterns. First of which is decomposition on the basis of business capabilities or business functions. These can be department wise breakdown. Let's take the example of a restaurant. We have supplier management service, we have consumer management service, we can have order management and fulfillment as a service, and we can have accounting, because these are different functions within that business. Next is we can decompose one step ahead than business capabilities using domain driven design. Decomposition can be done on the basis of subdomain. This is slightly more deeper and granular than the business capabilities. Take the same restaurant example. We used to have supplier management as a service, but we can break that supplier management system into sub services. For example, we can have management of suppliers in one service and management of inventory by those suppliers on a different service. Then we have customer management that can be done in two services separately. One is customer context management, and the other one is feedback management from those customers. Next is order management. Order management can have two verticals. One is managing the received orders, where we do creation and inventory update, and the other one is fulfillment. Fulfillment is related with delivery and logistics. Last is accounting, which can be seen as billing, which will include invoicing or payments, and we can have reporting. Reporting can be of sales, of refunds, etc. Next is we can decompose the monolith into microservices using strangler fig pattern. So in this, what we do is, when we have a monolithic system and we gradually break down that system one service at a time, despite of rewriting the entire application in one go, we do it single chunk by chunk. So all these patterns are not mutually exclusive. It means we can have any combination of these patterns in a single system. Next challenge was service communication. Microservice communication has two challenges broadly. One is how users, or you can say the front end APIs, will communicate with the system effectively without knowing how microservices are involved in catering to their requests. Second is how different microservices communicate with each other if required in a situation when more than one service is needed in fulfilling the user's request. So, combination of following design patterns can address the communication challenge effectively. First is the API gateway pattern. In this, user's request has to go through a single entry point, which is an API gateway. It is the component which does following: routing to take the request to the concerned microservices. It manages security centrally using authorization and authentication. It takes care of routing. It means to take the request to the concerned microservices. It takes care of security, manages authorization and authentication, logging all the incoming requests for analysis. Then it can apply throttling or rate limiting so that system is not abused, and it also can apply web application firewall to protect and restrict users by their IP or region or country, etc. Next is backend for frontend. We can have various separate backend layers for each frontend type. Example: mobile users, web users, or IoT. Backend for frontend forward request to separate customized microservices which can return specified responses. Example: mobile view can just require subset of data than its web counterpart. Next is synchronize communication. Synchronous communication between services is done when we need strong consistency. It happens using REST, HTTP, gRPC, or GraphQL. Lastly, we have asynchronous communication. When we require eventual consistency and we can wait for the fulfillment of tasks at a later period, we can utilize the messaging systems like RabbitMQ or AWS SQS or event-based systems like Kafka. Next challenge is data consistency. Every service in microservice architecture must have its own database. Thus, maintaining consistency in the system as a whole is a challenge, because for the software development team, the system is a set of microservices, but for the end customer, it's a single system. We can have following patterns to address this data consistency challenge. Database per service pattern. While each service can have its own database, the database can be different. It can be MySQL or NoSQL. Next is we can have a shared database, but this is NT pattern and should only be used as a temporary solution. Next is CQRS, which is Command Queries Responsibility Segregation. We design the system in such a way that it uses different model for reading and different for writing. This also means that read optimized database replica is used by read query model and write optimized database will be used for write models. Next is the Saga design pattern. This is important. This is a design pattern which handles the distributed transaction. A distributed transaction involves more than one service. Let's suppose we have a transaction that involves database queries to be run across DBs of three services A, B, and C. If the queries at B or C service fails, then we have to roll back the changes that are done in prior services. We have to write compensation transactions in this situation. More the services involved, more complex it becomes to write the compensation transaction. Last is event sourcing. It means we can store sequence of events that happen to generate the present state. For example, let's suppose we have order status which is delivered. So we need to find the sequence of events that changed or updated this status to delivered, so that we can easily verify and cross check at any time. This is a great way to verify and preserve the audit trail as well. Again, all these patterns can be the part of single software system, which means these are not mutually exclusive. Logging and observability is challenging because an error that occurred for a request could have happened on any of the services involved in fulfilling a particular request. In software systems, we have to be always eager to know what happened, when it happened, and how it happened, and will it happen again. To address these challenges, we should have a centralized logging system where we can log all errors and analyze them fast and in an intuitive way. Example for that can be ELK stack, in which we can visualize everything in Kibana, or we can use Grafana as well, or maybe a combination of these. For requests that has various services involved, we can implement distributed tracing. For the errors, can be done using Trace ID. AWS has a good offering, AWS X-Ray, for this purpose. Next is health check and circuit breaker pattern. So health check consistently checks if the service is okay to deliver the result or not, and circuit breakers are to be implemented in order to prevent cascading failures, which means by cutting off services that are failing, so that we can prevent the failure to happen again and again. Next challenge is distributed transactions. There can be failures at the network level, there can be failures at data layer or hardware failure or even logical layer as well. So mitigating for these failures include retry logic. Retry pattern can be used here. So retries can be done for the limited times, but retry should be done preferably in series, just like after 1 second, then after 2 seconds, then after 4 seconds, and so on. Next, we can have timeout pattern. We can always define a timeout on a service call to prevent blocking and network load shedding. Last is idempotency pattern for duplicate data prevention. We use a transaction ID for a request. If the request comes again and the ID matches with the given same result, in that case we will give the same response that was returned earlier. So far we have covered many useful patterns to address microservices challenges, and I hope it gave you a better understanding of how microservices are optimized in real world. Don't forget to like and subscribe to more such detailed contents.